Hello everyone, welcome back. In this session, we will learn how to compute slope and deflection for an overhanging beam using conjugate beam method. First, let me read out the problem. Determine the slope and maximum deflection at the free end of the overhanging beam as shown in figure below using conjugate beam method. So if we draw the deflection line diagram, it will be in this pattern. There are two deflections here. One at the free end, that is delta B, and another one is delta C as shown in the figure, and the slope we will get at the free end as theta B. Now in this problem, let us compute the slope theta B as well as the deflection delta C and delta B. So this is the overhanging beam. For this we need to draw the bending moment diagram. First let us consider the portion AB. There is a 20 kilonewton here. So the bending moment diagram will be in this pattern WL by 4. 24 by 4, it will be 20 kilonewton meter in this direction. This is for AB. Now let us consider now 6 kilonewton. Now this is the overhanging beam. First let us try to draw the bending moment diagram. Now first let us take the 20 kilonewton. So considering this portion AB, this works out to be WL by 4, that is 20 into 4 by 4. It is 20 kilonewton meter. Now considering this 6 kilonewton which is at the free end, let us try to draw the bending moment diagram. This will be 6 into 1, it is 6 kilonewton meter. So this is A, this is B and this is D. So now we need to add these two bending moment diagrams. It comes in this pattern. So top the loading is acting in the downward direction, at the bottom the loading is acting in the upward direction. So this is the M by EI diagram. This is the conjugate beam. As you can see that in the real beam at support A there is a hinge support. Therefore in conjugate beam also at support A we are having an hinge support. This is the real beam. Now intermediate support at B is transformed into an hinge in the conjugate beam, as you can see. The free end in the real beam, that is at point D, is transformed into a fixed end at D, as you can see in the diagram. So this is a conjugate beam, again loaded with M by EI diagram. So now considering this conjugate beam, we need to compute the slope and deflection. So this will be the pattern. VA will be acting at support A, and since B is a hinge, there will be two forces acting, VA in the upward, VB in the upward direction and VB in the downward direction, and at support D we are having VD. So now let me consider the half of the portion, that is AB. So drawing this bending moment diagram, I am taking only portion AB for computing slope at A and deflection at C. Now considering the portion AB, let us compute the slope at A and deflection at point C. Let me draw the bending moment diagram for only portion AB. This is point C. AC is having 2 meter and BC, the distance is also 2 meter. Let me consider this as area 1. Load acting in the area 1 at CG is W1 and this is the W2 acting at the CG for the area A2. So this is the VA and this will be the VB. Shear force at A plus shear force at B will be equal to W1 minus W2. So W1 will be equal to half into base is 4, height is 20. This is 20 by EI. This is 6 by EI. It works out to be 40 by EI kilonewton and W2 is half, base is 4 into height is 6 by EI. It works out to be by EI Newton. Substituting W1 and W2 in the above equation, that is equation 1, we will get VA plus VB is equal to 28 by EI kilonewton. Considering bending moment at B, VA into 4 meter minus W1 into X1. This, let me call this as X1. This one will be equal to 2 meter. Let me call this as X2. This X2 will be 1/3 of 4 meter. It works out to be 1.33 meter plus W2 into X2. So substituting the values of W1 and W2, we will get VA as 16 by EI kilonewton and VB as 12 by EI kilonewton. Therefore, theta at A or slope at A will be equal to 16 by EI kilonewton and slope at B will be equal to 12 by EI kilonewton. Now let us calculate the deflection at C. So now considering, in order to calculate the deflection at C, we will take only the portion AB. Again, let us draw the bending moment diagram. This is 20 by EI. This is 6 by EI. This is the point C. So at point C, by interpolating, the value becomes 6 by EI. The distance is 2 meter from BC and the distance of AC is also 2 meter. Let me call the load of this triangle as W3 and the distance is X3. Load from this triangle is W4 and the distance is X4. So the shear force VA is acting here and VB is acting here. Let me calculate the value of W3. W3 is half, base is 2 meter, height is 20 by EI. So it is 20 by EI kilonewton. W4 only this portion up to C. This is half, base is 2 meter, height is 3 by EI. It is 3 by EI kilonewton. Similarly, X3 is 1/3 of 2 meter. It is 0.67 meter and X4 is 1/3 of 2 meter. It is 0.67 meter. Now we know that bending moment at C gives us deflection at C. So bending moment at C works out to be VA into 2 meter minus W3 into X3 plus 4 into X4. Substituting the value of VA, W3, W4, X3 and X4, we will get moment at C as 20.61 by EI kilonewton. Therefore, delta C is also 20.61 by EI kilonewton. Now we will move on to calculate slope at D as well as deflection at D. Till now we have considered only portion AB. Now we will consider only portion BD. Consider only this portion. This is 1 meter. Let me call this W5, the CG distance from the support to D as X5. This is B. Now as you can see in the portion BD, VB, here it is acting in the downward direction, VD is acting in the upward direction. Taking summation of the vertical forces, we will get minus VB plus B plus W. This should be equal to 0. We already know that VB is equal to 12 by EI. We need to calculate W5 so that we can compute the value of VD. So W5 is equal to half into, this is 1 meter, height is, this is 6 by EI. 6 by EI, it works out to be 3 by EI. Let's call this as equation 2. Substituting the value of VB and W5 in equation 2, we will get minus 12 by EI VD plus 3 by EI is equal to 0. VD is equal to EI kilonewton. Therefore, at D is equal to 9 by EI kilonewton. Now we need to calculate the deflection at D, taking bending moment at D equal to VB into 1 meter. This is creating an anti-clockwise movement plus W5 into 5. We will get VB is minus 12 by EI into 1 plus W5 is 3 by EI into X5. We need to compute. X5 is 2/3 of 1 meter. It works out to be 0.67 meter. Substituting the value of X as 0.67 meter, we will get 10 by EI. Therefore, deflection at D is equal to 10 by EI kilonewton meter. Newton meter minus. Hence, the problem completed. Hence, the problem completed. So, we have calculated theta A, theta B and delta C using only portion AB, and we have calculated theta D and delta D considering only portion BB.